Hello, everyone. I'm delighted to introduce our research topic today. My name is Daeyoung Kim, and I'm in charge of algorithm research in BISTel's data science team. Our research topic is analyzing 2 terabytes of raw trace data from a manufacturing process. As far as I know, this is the first use case of Apache Spark for semiconductor wafers from real industry. In this presentation, we are going to explain how we apply Apache Spark to our product for smart manufacturing. Our presentation will be in 2 parts. First, I will introduce our company and its big data solutions. And then, Seung-Cheol Lee will explain 2 use cases of Apache Spark in semiconductor manufacturing: trace analyzer and map analyzer. I'm going to start with the introduction of our company. BISTel is a world-class provider of intelligent manufacturing solutions for all manufacturing industry, such as semiconductor, vehicle, chemistry, steel, and energy. BISTel was established in August 2000. Our headquarters is in South Korea, and R&D center is in Santa Clara, and our regional sales branches are in Austin, China, Japan, Singapore, and Europe. BISTel provides analytic and automation solutions based on artificial intelligence and big data to all manufacturers. At first, BISTel focused on developing solutions in the high-tech industry, such as semiconductor and display. And then we tried to expand our business areas into industrial manufacturing, such as automotive, energy, and steel. Our solution can be categorized into 3 parts: detect, analyze, and predict in the manufacturing process. In this presentation, we will focus on the BISTel's analysis product. Its name is eDataLyzer. As you can see, eDataLyzer consists of map analyzer, IntelliMine, and trace analyzer. Map analyzer is an advanced wafer analysis tool for effectively analyzing any map data. And IntelliMine is a data mining tool for root cause analysis. And trace analyzer is a parametric pattern detection tool for raw equipment data. In this presentation, we are going to explain big data-driven MA and TA. MA detects patterns automatically using clustering algorithms. By clustering such defective wafers, MA identifies specific clustered patterns. And it has important information that reveals the status of manufacturing process. In this concept, we need 2 big data-based clustering algorithms for processing thousands of wafers in short times. And trace analyzer provides in-depth root cause analysis to 2 parameters and less steps. And it is able to visualize the trace's behavior. TA can compute score by comparing normal and abnormal trace data based in a certain range. If we obtain higher scores in certain ranges, it means that there are some abnormal conditions in manufacturing process. So we also need 2 big data-based algorithms to calculate huge raw trace data. Therefore, BISTel has researched big data platforms and tried to apply them to our product for several ways. We use the 4 big data platforms: Hadoop, GPDB, Oracle VDA, and Spark, and successfully implemented the algorithm for big data version to our customers, such as Hynix, Samsung, and Toshiba. For comparing various big data platforms, we experiment performance tests in several ways. These results show the performance comparison between GreenFromDB and Apache Spark when we use our MA solution. As you can see, the graph, the performance of Spark is about 7 times faster than GPDB in running time perspective. So we finally select Apache Spark as our key big data platform. Now that we've covered our solutions and big data experiences, let's move on to the next part. Seung-Cheol Lee will explain more details about the Spark algorithms using in TA and MA. Okay, thank you very much.
Okay, firstly, it is a great honor for me to have an opportunity to be a speaker at Spark Summit, and I would like to share 2 solutions which are developed using Spark with you in the following slide. So let me introduce the trace analyzer, which is called TA. Before going into detail, I will explain terminology used in the TA. So the trace data is sensor data collected from a processing equipment. Let's take a look at this figure. A wafer is going through all this machine. This full procedure is called a process step. And in one process step, there are multiple sub-steps called recipe step. There are 4 recipe steps in this example. And each recipe step has sensor data that produce data indicating that machine status, such as temperature and humidity. For example, there are 4 recipe steps, and each recipe step has 10 sensors. Then we have total 40 sensor data in this one process. So we can hierarchicalize each step. In one process, there are multiple sub-steps, and while going through recipe step, the lot containing wafer is moved. Through this procedure, the wafer is processed. This scenario can be visualized in the right figure. It is more straightforward to understand. The x-axis indicates the time, while the y-axis is sensor's value. The full x region is processed, and it is divided into multiple recipe steps. And the line represents the wafer. If there are 100 wafers given, then there are 100 lines shown in this figure. So what the TA is going to do is that it can extract a sign that has a different shape between 2 groups. If the user gives a bunch of the trace data into TA as input, then TA result can inform you that you need to drill down the recipe step because it has difference between 2 groups. So it is a screenshot of the trace data. Let's see one row from a trace data. So for a process name, O21 LIT and number 1 recipe step, the wafer number 1 has 2 sensor values at this exact time. So basically, it is a little different between manufacturing companies, but almost the wafer size about 1,000 per one process and per one parameter. And each recipe step, there are 1,000 to 2,000 data points, which means that there are 1,000 lines, and each line has 1,000 data points per process. And note that some factors make trace data huge volume. If we have the number of parameters processed, wafer, then we have the trace data size is greatly increased. So let's do some calculation with the trace data. Out of these 4 fabs, let's take a look at the number 1 fab called array. The data frequency is 1 Hz, which produces the data point per 1 second. It has total 10 recipe steps, and average recipe time is 16 minutes, so the total duration is 160 minutes. Therefore, total data point in one process will be 160 times 60 seconds and 1 Hz, which will be 9,600 data points in one process. So, and if we analyze multi-parameter parameter multi-processes and multi-wafers, it is obvious that the data point is greatly increased. So to handle such large-scale trace data point, we choose the Spark because the Spark is the best way to process big data in batch manner. And the trace data, which is column-based, is easily manipulated by Spark's APIs. And also, it is easy to install and deploy our solution to our customer for their use. So let's move on to the next slide to see how we apply the Spark to our solution TA. So before applying Spark, we didn't use the big data framework. As shown in the figure left, we used the pure Java for calling TA logic, and we obtained the TA result. Because the data size is under gigabyte, it doesn't take too much time to finish the TA algorithm. However, the data size is increased. It takes a lot of time to return the result. Therefore, we applied the Spark to TA as shown in the right figure. We transform trace data into RDDs, and then the TA algorithm is executed in RDDs for each node. The user can access the RDDs and obtain the TA results through the wrapper layer. And we call this as a Naïve TA Spark version because we use the TA algorithm without any change except for distributing the data into RDDs. So I'm going to explain the Naïve TA Spark version in a pseudocode level. Firstly, we use the map to pair method in order to set trace data as a key value pair. Basically, the key is process step, recipe step, and the parameter, and the remaining are set as value, which are the wafer and its sensor data and time data. And then method group by can distribute the data across nodes based on the key we set. Then we call the TA algorithm in flat map function. The run trace analytic method executes the TA algorithm, and we can get the result, TA result. Most cases in manufacturing industry can process it using Naïve TA Spark version because the most parameters have small number of data points, which are 1 hertz, and the wafer size is not that large, which is up to 1,000 wafer. So therefore, the total number of data points in a process can be easily processed in a single core. However, I received a mail indicating that some parameters have a lot of data points, which caused the memory problem when we use the Naïve TA Spark version. While the program runs, some executors are lost due to the memory issue because there are too many data points in a certain recipe step. So recently, in manufacturing industry, sensors with high frequency are generated, and it produces huge volume for a single parameter. We call this parameter as the big parameter. And also, when the wafer size increases, the total data points are very huge. In one case, the wafer in a process is 400,000 wafers, and each wafer has 20,000 data points. Then the total data point will be 400,000 times 20,000, which exceeds the memory resources to be processed in a single core. So let's look at the code. And when we execute the group by key, too many data points are pushed into a single core. In addition, to call the TA algorithm, we use the Java object to hold the data point. While adding the data point into Java object, it exceeds the memory size of a single core. Therefore, we need a new Spark version. Naïve TA cannot process massive data points, and recently, sensor with high frequency is made due to the technology development. To process such a large-scale data point, TA for big parameter version is necessary. Our idea is that instead of just calling TA logic in a naive approach, we extract the core logic from TA module and apply it to Spark code. So we used the 4 ideas, and I will explain how we did using Spark in the following slide. First, before executing the TA algorithm, we added the batch ID to the key so that we can adjust the value size. For example, if we set batch size as 100, 100 wafers and its trace value are paired with key. The larger batch size we set, then the bigger data size we have, and the smaller batch size we set, then the smaller data size we have. In this way, we can adjust the value size in order to not exceed the memory resources in single core. Second, TA Spark for big parameter is key-based processing. It means that TA needs to compute some statistic summaries for whole process and also for a certain recipe step. When we need a statistic summary for a full process step, then we extract process and parameter out of all these keys and set them as a new key for later procedure. Also, when we need a statistic summary for a recipe step key, then we extract process, parameter, and recipe step out of all these keys. Since TA has lots of calculation based on process step or recipe step, we need to change the key based on our purpose. A second idea is using the collect method. I know that collecting the value is not recommended because it collects all the data points into driver node and it will degrade the performance. So to avoid it, we collect only statistic summaries, which are very small amount of data compared to the all trace data, and send them to the driver for broadcast. I will explain with the TA example. There are 6 TA modules, and one of them is called cleaner modules, which pre-process the low trace data for obtaining more correct result. In a cleaner module, there is a length filter step, which filters out traces that have unusual duration of process time. As shown in the figure, these 2 wafers are unusual compared to the other wafers. So to filter such wafer, 2 statistic values are required, which are mean and standard deviation. If we obtain threshold using mean and standard deviation and share this information across all the nodes, then we can filter out such wafer based on information we compute. Since we cannot use the TA logic without change, we use the 3 Spark APIs to extract the information we need from the TA logic. I will explain how we did in the following slide. So to obtain the median and standard deviation values, we need to identify the wafer's length. Since we store all the trace values, it is easy to obtain the wafer length for each node. We set the process step as a new key and set the wafer and its length as a value for each node. Note that the key is a process step, not a recipe step, so we need to aggregate the value to obtain the wafer length for a process. So we use the reduce by key to aggregate the values into one. For example, wafer 1 has a length of 65, and the same wafer has 88, which are stored on different nodes. It means that the wafer has same process step, but different recipe step number it has. Since we set a process step as a key in the previous, we can obtain the total wafer's length for the process step by summing up each wafer length computed based on the recipe step. So after obtaining wafer length for a process, we can apply the TA core module. This PK variable contains the process step key, and the variable values contains all the wafer's length in a process. The filter by length method is extracted from the TA module, so we can apply it in the map to pair function to obtain the threshold based on the mean and standard deviation, which are computed from all the wafer's length in a process. This is a very small amount of statistical summary, so we can collect and broadcast them to filter out the wafer that looks unusual. So in this way, we compute the threshold and collect and broadcast them to apply it to all the nodes. Whenever we need to compute the threshold or some statistic which need to be shared across the node in many TA modules, we use this strategy I explained for TA cleanup step. So here is another interesting example. Also, there is a step to detect the outlier in a process. As shown in the figure, these data points are above compared to the other values. So these values are considered as the outliers and need to be removed before computing the TA scores. To detect this outlier, the median value needs to be computed. Before obtaining the median value, all the data points need to be sorted. However, it is not easy to sort all the data points in a single node, which exceeds the memory source. So we computed the approximate median value instead of sorting the value to get the median. By using the frequencies for being in histogram, we can obtain the approximate median value, which is located in the middle of the distribution. We follow the similar procedure as we did in the length meter step. Firstly, we use the map to pair to extract the information from the trace data. In this case, the information we need is the bin count for each data point. And we use the reduce by key to sum up the bin counts and collect the histogram. This is very tiny data so that the shuffling size is very small. And also we can compute the median by looking up the data distribution of this histogram. Since we used collect method too many times, we have to cache the trace data to prevent fetching the data from disk whenever the action command is performed. So we persist Java object of trace data to disk level so that we can prevent data load. As you can see this screenshot, if we do not cache, Spark tries to fetch the data from disk whenever the action is performed. So we choose the RDDs because we need to scan all the trace data values to get the statistical summaries. So the advantage of Dataset, which is able to fetch selected data by query, is disappear. And it is hard to manipulate trace data using SQL. There's not only basic statistics such as mean, max, and average, but also there are advanced in-house developed algorithms in TA modules. So we tested TA with 2 terabytes of trace data, and let's see a demo. So we store the data in Hadoop file system, and we can see the data located in the Hadoop. So there is the trace data I inserted into Hadoop and then run the TA algorithm. So I skipped the middle since it takes too much time. And you can see the results saved in the Hadoop file system. So there are lots of TA results saved in the Hadoop file system, and we can import this result to our product eDataLyze, and you can see and interpret the TA result in eDataLyze. On the right side, there is the trace data divided by recipe step, and the left side, we can see the TA score, which represent how different two groups are. So we can see the score for each recipe step in the left. So as you can see in the parameter 10 and recipe step number 3, there is a distinct difference between focused and non-focused data, which has the highest score. So you need to examine the certain recipe step. So by analyzing low trace data, it is capable of detecting subtle anomalies on sensor data. So this is the stage of Naïve TA Spark version. Since the Naïve Spark just called the TA core algorithm, it doesn't have many stages required for running the TA. For the new Spark version for big parameter, the number of stages increased due to the action command we used. Note that the amount of shuffling data is not that large, indicating that we extract the necessary statistical summaries from low trace data. And data loading from disk takes almost in running time. So in summary, we developed two TA Spark versions. We can choose one according to the trace data characteristic. When there are lots of parameters which contain small number of data points, then the Naïve TA Spark will be suitable. And to process large-scale data point in a few parameters, our new TA Spark for big parameter version will be used. This result is estimated on 12 virtual machines in our company. So if we add more worker nodes, the running time will be enhanced. So let me explain the map analyzer, which is called MA, and its use case. Map analyzer is to find the defect cluster pattern by clustering wafer maps. As shown in the figure, each wafer map has defective chip color in the red in a wafer. And using the hierarchical clustering algorithm, you can find cluster pattern from wafer map. Here is a sample of the MA dataset. The defective chip contains a list of coordinates in a wafer map. You can visualize the defective chip as a wafer map as shown in this figure. Since the manufacturing system produced lots of wafer map in recent, we use Spark to identify clustering pattern from massive wafer map. To execute hierarchical clustering algorithm using Spark, we firstly generate a key value pair by calling map to pair method. Key consists of a batch ID and the parameter, and the values are lot, wafer, and its defective chip. After group by method, the wafer map which belongs to the same parameter are put together, and then we apply the standard hierarchical clustering algorithm in map to pair method. To cluster massive wafer map, we add the batch ID. As I mentioned in the previous slide, without this batch ID, the size of wafer map to be processed in a single core is too large. So for each batch, we apply the hierarchical clustering algorithm and merging the clustering result, which has the same parameter. By doing this, we can obtain the clustering result, although it is a little bit inaccurate sometimes. So here is the demo, which shows processing 26 parameters containing about 120,000 wafers. Considering monthly wafer production in a fab is about 30,000 wafers, clustering more than 100,000 is the larger size in semiconductor manufacturing. In the map data, we can see defective chip and as a coordinator along with lot and wafer. So we run the MA algorithm. And also, same as TA, we found the result in the hard file system, and we can import the result into eDatalyzer to visualize it. So this is the MA result from eDatalyzer. We can various clustering result according to the parameters. When we click the clustering result, we can see the original wafer map data that is used for obtaining the clustering pattern. So there are maybe about 20 wafers that is used to generate the cluster. However, the MA employing batch mode has some limitation in clustering. We have received a complaint from one of our customers. They said that the similar pattern cannot be found when the number of wafers is 7,000. However, when the wafer size is 15, then they can detect the pattern. Because we apply batch to clustering algorithm, if very similar two wafers are assigned into different batch, then it fails to detect the clustering. These two wafer maps are very similar, as you can see, And this normal pattern is the cluster 1 we want to detect. However, it cannot detect when the wafer size is 15 because the different number of batch ID. So while trying to resolve this issue, we found a paper about the hierarchical clustering algorithm which performs on distributed machine. It is also presented in Spark Summit 2017 by Chen Jin. She presents a scalable hierarchical clustering algorithm, which is SHCA. It makes it possible to obtain an accurate clustering result on distributed machine. By converting the hierarchical clustering problem into finding minimum spanning tree, correct clustering result can be obtained even on the distributed machine. So in order to apply SHCA to our semiconductor domain, we designed the key value pairs as follows. Key is the wafer map ID, and value is its defective coordinate. And to compute the minimum spanning tree, the distance between two wafers should be computed. We used our in-house developed algorithm to compute the distance between two wafers and obtain the similarity score between them. So firstly, in the original MA, which employs batch, when we click the clustering result, we can see the 14 wafer which construct the clustering result. Another disadvantage of the MA batch is that it cannot adjust the parameter C, which is the cutoff value for dendrogram. Since batch process includes multiple time of clustering and merging procedure, it is very hard to change the cutoff value C for parameter. Therefore, it has a limitation on detecting more specific and accurate clustering pattern. However, in the new RMA, we can adjust the parameter easily so that we can detect more specific pattern by adjusting the parameter value C. As shown in the figure above, the white one represents the defective chip, and the black background is the wafer map. Even for the small number of wafers, such as 2 or 3, clustering pattern can be found very well. So this clustering, as you can see, the first cluster pattern is obtained by clustering only just 2 wafer map. This result showed the Spark stage of new MA. For about 100,000 wafers, the prim algorithm, which computes the hierarchical clustering for each node, take up the largest proportion of the running time. We compared two MA versions using different MA dataset. As the number of wafer dataset increased, the new MA take a lot of time because it needs to do calculation for obtaining minimum spanning tree. However, in MA batch, it avoids handling large number of datasets by adapting batch, so running time is more faster than the new MA version. Therefore, in our company, we are considering use both of them depending on the number of wafers to be analyzed. So it is our summary. MA using SHCA is accurate than the batch MA. However, the running time of the batch MA is more faster than that of the new MA. In manufacturing industry, we suggest them to use both of our MAs according to the number of wafers. So it is our conclusion. This is the first use case of Apache Spark in semiconductor industry as far as I know. The terabyte of trace data is processed. Note that all the data is scanned and it is used for computing summarizing statistics. And also, we achieved the hierarchical clustering on distributed machines for semiconductor wafers. Our research is able to help engineers analyze data generated from manufacturing process. So special thanks to our team member, especially Andrew, who is my team member working in BISTel Korea. And thank you for your attending. Thank you.
So if people have questions for the speakers, there's a mic over there, and also I can run around with this one.
Quick question on the, you mentioned that the edge actually represented the distance between the two wafers. Yeah, edge represents the distance between wafers. Perhaps I would have probably thought that you were looking at the distance between, you are identifying the failing chips on the wafer,
Yes.
right? So you're trying to establish some kind of relationship amongst the failing dies, the
Yes.
failing chips, in terms of sharing similar parameter for some step in the recipe process, right? In the step of the recipe. So how does the distance between wafer capture that relationship? Can you just explain that, please?
So we use the basic statistics, such as the summation or the defective chip in a row or in a core, and we compare these two wafers, how they similar.
So I guess, what's the intuition behind the distance between wafers representing that relationship to identify commonality amongst the failing patterns? And what's the intuition behind it? Still not clear to me.
As you know, when the just two wafers look similar, we just check the defective chip each row, and then compare how many defective chip for each row between two wafers, and then get the score. By using this procedure, we can compute the similarity score between two wafers.
So when you compute the distance between the wafers, you said you do a sum of row and column and
Yes.
find the difference.
Yes, yes.
A lot of times the wafer patterns get rotated. How do you handle that?
Actually, most cases didn't work well, but
Okay.
in our data, which has the defective chip, has some specific pattern. So in this case, our distance metric is working well.
Okay. Yeah. That's a common challenge that we are facing as well. So yeah.
Hi, thanks for the talk. I saw one of your slides, you mentioned like you were doing a Fourier transform and you chose to do RDDs instead of data frames.
Mm-hmm.
Can you talk a little bit about why RDDs are better than data frames for like complex algorithms like the Fourier transform?
Sorry, I didn't understand.
Yeah, sorry. So I saw one of your slides that you talked about the fast Fourier transform and you chose to do like RDDs instead of data frames.
Okay.
Can you maybe talk a little bit about why that's why you made that choice?
So as you know, the trace data characteristic, we need to know the statistical summary. To get the statistical summary, we need to scan all the data points which is stored in the disk. So in the case, when we use the SQL, when we query our data, in our opinion, the data which is selected by the query is loaded to the memory. But in our trace data TA case, we need to scan all the data points, not the partial data point. So the advantage of such a data set is weakened because we need to load all the data points to get the statistical summary. So we use the RDD instead of a data set.
Any other question? All right. Well, let's thank our speakers once again. Thanks so much.